students, myself Brinda Patel, Assistant Professor in Computer Engineering Department at Sri Swaminarayan Institute of Technology. So today we are going to start Unit 6 of Image Processing, which is Color Image Processing. So outline is, first we will see about introduction, then image compression model, error-free compression and lossy compression. So let's start with introduction. So images contain extreme amounts of data, like 512 by 512 image is made up of 0.25 into 10 raised to 6 pixels with the 1 byte per color, which is already resulting in 0.75 megabyte of data. So at 25 images per second, 1 minute of video, that resolution already yields 125 gigabytes of data. So scanning an A4 means 210 into 297 piece of paper with 300 dpi means dots per inch in black and white gives 875 megabytes or 11 megabytes. Scanning in 3 colors, which gives 26 megabytes. So there is an obvious necessity to compress images for both storing and transportation over the communication channels. So in image or in general data compression, we make use of the difference between information and data. So information is actually essential for an image or an data set. In that we really need to have, for we would like to process with it. So what that data information is, it is depends on what the further use of image will be. So whether satellite photo is used by a agriculture specialist to check the cultivation crops or by a geographer to make the urbanization of rural areas, the relevant information in the image is different for each purpose. So this data compression algorithms are distinguished into two classes, loosely and loosey. So with the looseless, the original data can be reconstructed exactly from the compressed data and the original data remains intact. So here we make the use of these compression computer programs, but it is also often desired for images. With loosey compression we cannot reconstruct the original data, therefore there is a loss of data. So it must be made sure that the relevant information remains intact, and that depends on the further applications that one may want with the data. So in general, loosey compression methods reach a higher compression than the looseless methods. So to access here the loosey compression methods on the suitability for certain applications, so we often use quality matrices G of xy, which is decompress means compress of f of xy after compression f of xy. So E square RMS is equal to 1 upon Mn and sigma G of xy minus f of xy raised to square. So SNR RMS is equal to 1 upon Mn sigma G xy square E square RMS. So another criteria which is based on the applications of the images, which can be objective or subjective. For example, judgmental by a panel of human observers could occur in terms of as a excellent, good, acceptable or poor. So other criteria for determining the suitability of a compression method for a certain applications, which are the attained compression ratios, the time and memory needed for the attained compression ratio, and the time and the memory needed for decompression. And other three types of data redundancy are used to design data compression methods, which are coding, interpixel or interframe for a series images, and application specific, for example psychovisual for a viewing of images by people. So a code is a system of symbols which contains letters, numbers or bits, is used to represent a units of information in a set of events. So for each piece of information or event, an array of code symbols, a code word is credited. For example, we usually represent each gray value with an equal amount of bits like 000, 001, 010 up to 111, which is the binary form of 0, 1, 2 up to 7. So when certain gray levels occur more often than others, so code of different lengths can be used. For example, 01, 10, 11 up to 000, 000. So this can be placed directly after one another to be decoded again. So you must know that these codes are used for and which gray values they represent. So depending on the distribution of the gray levels in the image, code with unequal lengths may result in either a higher or a lower compression. So neighboring pixels usually have similar gray or color values. For example, in binary image, row of zeros or ones occurring in the one scan line can be represented as a pair, means value and length as 0000, 111, 111, 111, 111, 111, 00000 as of this value 04, 16, 02, 18 and 05. So here there are many variations in the representation and the storage of their pairs. So these are the known as a run length encoding RLE methods, which is also used for sending faxes. So in the series of images, object written on subsequent images slightly displaced, a part of an image can then often be identified as a being slightly displaced from the previous images. So this idea is used in MPEG standard of comparison of color video images. So with the psychovisual redundancy, we use the fact that the eye doesn't make much of quantitative analysis of the gray or color values of every pixel, but is more attracted of features such as edges and textures. So now let's understand about model. So in a general system model for compression and decompression is here we can see source encoder, channel decoder and source decoder. So it is customary to use names encoder and decoder which have its roots in the field information theory. So it has rather than names as a compressor and decompressor if the transmission to storing channel is error free. The channel encoder and channel decoder are omitted. Otherwise, extra data bits can be added to be able to detect. For example, parity checking, cyclic redundancy checks, or correct the error, means error correcting code for the memory errors. So often we are using special hardware. So here with lossless compression, it holds that gxy is equal to f of xy. Now a general model for source encoder. So here the mapper is transforms the data to a format suitable for reducing the interpixel redundancy. So this step is generally inversible and can reduce the amount of data used for run length encoding, but not in transformations to the Fourier or discrete cosines domains. So the quantizer reduces the precision of the output of the mapper according to the determined reliability criteria. So this is specially reduce psychovisual redundancy and inversible. So it is therefore only used for loosey compression. And symbol encoder makes a static or variable length of code to represent the quantizer's output. So it reduces the coding redundancy and is reversible. Now channel, so symbol decoder and inverse mapper. So here the general model belonging to the source decoder is here, and the inverse for the quantizer has been left out. So here the general of information is modeled as a statistical process that can be measured in much as the same manner as the institution of information. So an event E with probability P of E has I of E is equal to minus log R P of E, which is R a unit of information, and P of E is equal to 1 by 2, then I of E is equal to minus log 2 by 1 by 2 is equal to 1 bit information. So if a source generates symbol AI with the probability of P of AI, then the average information per output is H of Z is equal to minus sigma P of AI log R P of AI. So this is the insecurity of entropy of the source. So this is the maximal when every symbol has an equal probability as 1 upon n. So it indicates the minimal average length for R is equal to 2 in the bits per symbol. So it needed to code the symbols. Now error free comparison. So for many applications this is the only acceptable manner, such as for documents, text and computer programs. So this is often used for images because they are already an approximation of reality with the spatial and intensity quantization and errors in the projection system. So now first is Huffman coding. So this is a popular method to reduce the code redundancy. So here the symbol are coded one by one. An optimal code for the set of symbols and probabilities is generated, right? So first one is block code. So every source symbol is mapped to a static order of code symbols and instantaneous code. So every code is decoded without reference to the previous symbol and is uniquely decodable. So it can be generated like this. The two symbols with the lowest probability are repeatedly combined until only two are composed. So the symbol left over here, this get codes like 0 and 1. So the components of the composed symbol get A0 or A1 behind it. So these are the symbol and these are the probability of it. Code, probability, code, probability, code and probability. Now so another one is Lampel-Ziv coding. So this translates the variable length arrays of a source symbols to a static code length. So the method is adaptive. The table with the symbol arrays is built up in one pass over the dataset during the both compression and decompression. So variant on this, by Welch is used Unix complex program. Just as Huffman, this is symbol encoder which can be used both directly on the input after a mapper and quantizer. Next is run length encoding. So many variations on this method are possible. For facts are based on this. So the run lengths themselves can be coded as independent variable length code, possibly separated for black and white if the probabilities are very different. So in 2D, we can use the fact that black and white transitions in consecutive scan lines are correlated, means relative address coding and counter tracing in several variations. Now bit plane decomposition. So a gray value image is divided into m into n large blocks, right? So here a gray level image of 8 bits can be transported to 8 binary images, which each need to be coded independently by a suitable code. So the most significant bits contain longest runs and can be coded using RLE methods. So the least significant bits contain noise. So here the RLE will not yield good results. Now constant R coding. So the gray level value is divided into m into n large blocks which are black, white or mixed. So the most probable type of block gets the code 0, the others get the codes 10 and 11, and the mixed blocks are followed by a bit pattern of it. So a variant of quadratry where the image is divided into 4 quadrants and mixed quadrants are further divided recursively to attain 3, then it is flattened. Now predictive coding. So here, starting at the previous source symbols and pixels values, the next value is predicted and only define the difference with the real values is passed on. For example, the predictor can be Pn of round I is equal to 1 sigma raised to n ai f n minus I. So with the ai, a well chosen coefficient for the first n values fn must be passed on, and if m is equal to 1 we get the differential previous picture coding. So for the 2D images, the row are consecutively placed in the model like this. So we would also use a pixel, right, from this row. For example, p of xy round a1 f of x y minus 1 plus a2 f of x y minus 1 y. So here, to make e of xy as small as possible, however a good initiation will become more difficult. Now lossy compression. So lossy predictive coding. So a quantizer that also executes rounding is now added between the calculation of prediction error en and the symbol encoder. So the it maps en to a limited range of values qn and determine the both amount of extra compression and the deviation of the error free compression. So this happens in a closed circuit with predictor to restrict and increase the errors. So the predictor does not use en but rather than qn. So because it is known by the both the encoder and the decoder. So the delta modulation is a simple but well known form from it. So Pn is equal to alpha Pin with alpha less than 1. So here pi stands for predictor input and Qn is equal to beta sin En and can be represented by a 1 bit value minus beta or plus beta. So here the disadvantages are so-called slope overload because a big step in Fn must be broken down in a smaller steps beta. And the granular noise because the step of plus or minus beta can be made repeatedly. So with the differential postcode modulation DPCM, Pn is equal to I is equal to 1 sigma m into alpha I Pi n minus 1. So under this assumption that the quantization error En minus Qn is small, so the optimal values of alpha I can be found minimizing like this E square n. So instead of one level, the quantization can be also be the L level stepwise Lloyd max quantizers. Transformation coding. So a linear reversible transformation maps the image to as a set of coefficients which are then quantized and coded. So often small sub images are used like 8 by 8 or 16 by 16, and small coefficients are left out or quantized in less bits. So for the DFT, discrete cosine transformation, and Walsh-Handmer transformation with 8 by 8 sub images where the smallest 50% of the coefficients are left out. So the DCT is often the best of the three for natural images. So DCT also has the advantage for DFT that there are less discontinuities in a sub images. This is less restrictive when seen by the human eye. So the coefficient can be quantized in the less bytes by dividing them into the certain optimal values. A higher frequency and the higher frequency, the larger the number. So the DC means frequency zero component is often treated separately by the symbol encoder because this larger than the other coefficients. So JPEG makes use of 8 by 8 sub-images, DCT transformation, quantization of the coefficients by dividing with quantization matrix. A zigzag ordering of it followed by a Huffman encoder separately for DC component. So these are the standard coding tables and quantization matrices. Right? Thank you.